Welcome back to the series of lectures on high-performance scientific computing. Today we'll start looking at how these high-performance machines actually function in trying to model any sort of phenomena, whether it be natural or any artificial phenomena. So usually we resort to something called as numerical modeling. As I had described earlier, that there is some complex or maybe simple phenomena which needs to be studied. And the question that we need to ask is, why do we need numerical modeling in the first place? As I said, analytical solutions are not easily available and in most cases are not achievable at all. These complex or not so complex phenomena are modeled using partial differential equations, and closed form solutions of these PDEs is not easily available. So what do? We resort to breaking them down using the process of numerical modeling, and we ask ourselves, what are the steps involved? So typically you have some phenomena which is, for example, could be fluid flows, heat transfer, electromagnetics. This is all from the natural side of things. From completely artificial side of things, you could think about the behavior of financial markets or commodity prices. All these are things that we would like to study. We then proceed to put what we call as governing equations or different partial differential equations in modeling this phenomena. For example, we have the Navier-Stokes equation, which deals with fluid flow. You have the heat equation, which deals with heat transfer, Maxwell's equation, which deals with electromagnetics, so on and so forth. As mentioned several times, these PDEs do not have closed form solutions. So hence we resort to breaking them down into a series of algebraic equations using some sort of numerical method. You could have different kinds of numerical methods like finite difference, finite volume, Galerkin, lattice-Boltzmann, so on and so forth. Let us now try to understand what is really happening. Now let's think about a simple problem where we want to look at the temperature distribution in a city. This is a classic problem in trying to predict weather. Now, there will be a few questions that we would like to ask. Like, if I want to model and try to get the temperature within the city, what are the factors that I really need to consider? Obviously, you would look at the amount of incident solar radiation which is coming in from outside the atmosphere. You would look at other factors such as wind. You would look at factors such as artificial conditions like of roads, building, natural conditions such as tree cover, water bodies, so on and so forth. Now, what are the different levels of details of modeling that we need to get to? Do we really need to model each and every molecule of air which is in circulation at that point of time? It's possible to come up with a model where we are modeling each and every molecule which is there. But you will very soon realize that A, it is computationally unachievable because of the current computing limits. B, it's probably wasteful as well. You really do not need to track each and every molecule to reasonably predict what the weather is going to be for the day. The other dimension that you would like to look at is probably time. As we know, temperature varies during the day. How often do you want to notify the change in temperature? We could look at it every hour, every half an hour, every minute, every second, every nanosecond. So the question is, depending on the application that we are really looking at, we will then implement different models. Then what comes is, what are the assumptions we make when we write the governing equations? For example, when we use Navier-Stokes equation to say model some sort of fluid flow, we typically assume what is called as the continuum hypothesis. We are not really looking at the individual motion of each molecule in the fluid. We are considering what is called as the macroscopic phenomenon. So we are able to take, because of the macroscopic phenomena, some sort of continuous derivatives. Now, when we do this, we are actually losing some information, right? Because in reality, if you keep going down to the molecular level, the fluid is actually a discrete set of molecules. But then it's okay to make an assumption that it behaves as a bulk, because the answers that we are looking for will be achieved within the range of satisfaction. Similarly, so the first error that we make is when we take the phenomena and we write down the governing equation, we are actually introducing some sort of error over there. So we have already introduced an error the moment we put down a governing equation. We make assumptions like the material that we are working with is uniform. For example, the fluid with which we are working, we assume its properties such as viscosity, density is more or less uniform and is only dependent on temperature maybe. That itself is a leap of faith. Now, so we have already made an error when we go from actually modeling the phenomena to writing down the governing equations. Then we say that the partial differential equations cannot have a closed form solution, and hence analytical solutions are not feasible unless there are some very specific assumptions to be made. So we resort to taking these PDEs and converting them into algebraic equations. The moment we do that, we introduce another error. The example that I can think of is if you think about approximating a derivative. Let us say that I want to compute f dash of x at any point. So one of the popular ways of doing it is something called as a central difference method, where I take f of x plus h, f of x minus h upon 2 delta h, or rather 2h. Okay? So this is one way of computing this derivative, a numerical way of computing this derivative. How does this come about? We derive this from the fact of the Taylor series expansion, where we have f of x plus h is equal to f of x plus f dash x over h plus f double dash x over h square and 2 factorial, and so on and so forth. There are some terms over it. I may not be completely accurate with all these terms, but you understand the principle that there are these higher order terms, and then we tend to neglect these higher order terms, and then we get something of some second order accuracy. So this is where we again, introduce another source of error. So we have error which comes in at the phenomena, wherever the phenomena is. When we write down the governing equation, we introduce an error. Then when we take the governing equation and we convert it into a numerical method by approximating the derivatives, we introduce another error. And the last error that we introduce is actually while doing the compute. So if you think about it, we now have a set of linear algebra equations which need to be solved on a computer. But even on a computer, you have what is called as finite precision. A number is described only with a certain amount of accuracy, a certain number of digits. Anything less than that, you have essentially what is called as round off error. And this is a computing error that we introduce, or what is called as the precision or / arithmetic error. So we have errors adding up from the accuracy of the governing equation, from the accuracy of the numerical method, and the arithmetic precision. The entire game of numerical modeling is to sort of balance all these errors, or rather have reasonable parity between these errors. For example, let us say that we have an incredibly accurate computer which is able to give us precision of the order of 10 raised to minus 32, or maybe even 10 raised to or minus 100. But if my method over here is not super accurate for converting the governing equations to numerical method, and it introduces errors of the order of 10 raised to minus 2 or 10 raised to minus 4, then having a computation of the order of 10 raised to minus 100 serves no purpose. Similarly, when I'm writing the phenomena and the governing equations, if I write the phenomena in a very poor manner, like for example, if I'm trying to model the weather of a city, and I assume that the viscosity of air is not dependent on the temperature, right? And it just has uniform viscosity. I've introduced a big error over here, right then and there. And now that would cause a lot of issues. So then having a compute again of supreme accuracy doesn't matter. The converse is also true. Let's say that I have an incredibly high order method, which I have a numerical method which going back to this set of equations, I take more and more terms from here. I have lots and lots of terms over here, and I have a method which is very, very accurate, maybe 16th order accurate or 7th order accurate or so on and so forth. The thing is, if my computer is able to do only single precision calculations, is able to have accuracy only up to say 10 raised to minus 8, then there's no point having a 16th order method if my precision over here is going to be of the order of 10 raised to minus 8. Similarly, there's no point having an extremely high order method over here if you're going to make basic assumptions like viscosity being constant and so on and so forth, given the nature of the problem. Okay, so the entire art of trying to do numerical modeling is sort of balancing these three sets of errors where all of this becomes sort of meaningful. We also need to realize what is really important as a piece of information. For example, when I'm computing the temperature in a city, is it important for me to get it to what decimal accuracy? Does it matter whether the temperature I describe is 35 degrees Celsius or is it 35.231579? I think 35 degrees Celsius is good enough when it comes to human comfort. But when it comes to, say, maybe a biological process or a chemical process that you're trying to control in a controlled environment in an experiment, maybe more degrees of accuracy is important, right? So probably you will need maybe 2 decimal places or maybe 3 decimal places. It all depends on the process that you're trying to do. Similarly, let's say that I'm an aerospace engineer and I'm trying to look at the lift or the coefficient of lift on an airfoil. I'll be looking at this coefficient with certain degree of accuracy. So do I get a coefficient of lift of 0.97, 0.95, 0.98? It does matter. But if the accuracy is much lower than that, if it's somewhere like, it's either 0.2 or then 0.3, if I have that sort of least counts, maybe it's not that great. Similarly, if it has 8 digits of accuracy, that's again sort of an overkill. You do not need that much information. So here is where you need to use a judgment as an engineer to figure out what level of accuracy is required for what kind of problem that you're trying to solve. This has direct impact on the effort in the computations that you put as well, and in turn it has the the effect on the cost of the computation. Now let's start looking at a simple problem. Let's think about this as a steady state heat conduction problem. You have a square plate. The 4 edges of these square plates are kept at certain specific temperatures. The top edge is kept at a constant temperature of T0. The left edge is also kept at the same temperature T0, whereas the right and the bottom edges have a linearly varying temperature from T0 to infinity. Our objective is to try to find out what the temperature distribution is internally within the plate. So first of all, we need to write down what the laws of conduction are. We also need to make a few assumptions. One of the first assumptions that we will make is the fact that the plate is of uniform material and hence has sort of uniform thermal conductivity. It's quite possible that the square plate, even though it might be of the same material, could have voids, could have fractures, could have different thicknesses, could have some material anomalies which cause the thermal conductivity to change within the square. But we are taking a leap of faith here again, saying that the material is fairly uniform and the thermal conductivity is constant. So what is this? How is this phenomena modeled? This phenomena is modeled using what is called as a Laplace's equation, which is shown over here, where the partial derivative of t with respect to x, the second partial derivative of t with respect to x, plus the second partial derivative of t with respect to y is equal to 0. Now, since this is the other assumption that we have made is that this is a two-dimensional problem and the temperature does not vary in the z direction because this is a thin enough plate. Now, the next thing that we need to do is to discretize this plate in the sense that I will now take information at finite number of points within the plate. Again, what spacing of points I should use depends on how accurate I want the answer to be and how useful that data is going to be. As I said very clearly, let's say that this plate sort of represents the grid of a city, and these are different locations in a city. Let's say that we took a very flat city in the country and we sort of modeled it as a plate and we're just looking at heating from some fire which is coming at the edge of the city. Do you really need to know the temperature difference which is 10 meters apart or 100 meters apart or 1 kilometer apart? That all depends on the nature of the problem that you're trying to solve. So the choice of number of points again will depend on the application that this is there. So let us assume that we have discretized this now with certain finite number of points. You have I number of points going from in the x-axis direction and you have j number of points in the y direction. The second assumption that we are doing is that all these points are uniformly spaced. It's not necessary that these points need to be uniformly spaced, but we are going to have them uniformly spaced. We address each point by their indices I, j. The next step is to discretize this equation at around a single point I, j. So the partial derivative with respect to x using calculus is now discretized as this term ti minus 1j minus tij plus ti plus 1j divided by delta x square. The partial derivative with respect to y is now tij minus 1 minus tij plus tij plus 1 by delta x square is equal to 0. Now, for all the points ij, this equation is for a single point I, j. As you would realize that there are several points as I spans from 0 to n and j also spans from 0 to n. You will have n cross n number of such points and you will have n square equations. You will have n square unknowns and n square equations. And you will assemble all these equations in the matrix form, which is Ax is equal to b, and then you can choose any linear algebra solver, iterative or direct, to solve. We have already discussed in a previous lecture that iterative solvers are more efficient when you come to doing this problem. So what do? One writes a computer code. So we are not going to describe the entire code over here. We're going to sort of just depict a code over here which says that we write this code which is going to create all this sort of assembly of these equations, discretization, and then finally doing the linear algebra solve for getting the solution. You then compile and execute this program. Once you compile and execute this program, you get some nice colorful plot which will give you the temperature variation in x and y of this plate. But what really happens? What happens in between? That's the question we need to ask. We realize that computers really understand only zeros and ones, and they're actually incredibly stupid machines. Microprocessors, which build most of these computers, have simple logic circuits which perform only simple arithmetic operations such as add, mul, sub on these binary numbers. There might be a few more complicated logic circuits, but none of them will be able to solve the partial differential equation directly. So each operation now consists a set of instructions which the processor has to perform. So what does this look like? Our calculation then, remember we have about n square unknowns, it is broken down into thousands, probably even millions of these instructions which are then executed. All these operations of taking the computer code, breaking them down into millions of instructions and then being executed on a microprocessor are basically hidden from the user, because it would be very difficult for a human being to write down even a simple code directly in assembly language for a simple problem such as the temperature distribution on a flat plate. So it's time to dive into the rabbit hole. We take the blue pill or the red pill, this is a quotation from a very famous movie, and figure out what's going on underneath the hood. So this is an image of the precursor to inputs to a modern day computer. Many of you might not recognize this, but this is what is called as a punched card. The punch card would actually be the set of instructions that a computer needs to execute based on the program that one writes. So in the days gone by, before we had keyboards and other inputs devices and higher levels of programming languages, one had to feed in the instructions using these punch cards by punching holes which would then be read by the computer. Each program would be a stack of hundreds of such code, these punch cards with different perforations in it. Thankfully, we do not have to program using punch cards anymore. What do is we write in application software which is written at a higher level language, something which human beings can understand. We do not have to write our code in machine code. So what we do is that we write our algorithm in a high level language, and then the compiler translates this high level language into machine code. There's also other software associated called system software, so where the operating system handles different things. As I mentioned earlier, that in the past you would actually have to feed sort of paper tapes and punch cards to give the instructions to the computer. Today we no longer need to do that. We have devices like keyboards, mice, even touchscreens to handle input and output. We also have ways to manage memory and storage. Remember, the programs that you write need to be stored somewhere. The data that needs to be input needs to be stored somewhere. We also have other tasks such as scheduling different controllers and sharing resources, because your program is not the only program that is actually running on a computer, right? So when I write a code and execute it, there are many other things that are happening on a computer, including things which the users will be doing, like say I would be having a web browser open in the background. There could be things which the operating system is doing, like keeping all the different peripherals and the hardware up to date and to keep checking whether they're actually working. And the bottommost layer of this is the actual hardware, which has the processor, the memory, the input-output controller, so on and so forth. So if you really look at it, the entire computer system layer looks at your bottommost part is the hardware, the machine that you're actually running on it. There's some sort of program called the system software on top of it, which sort of interfaces with this hardware, keeps a control of this hardware, keeps monitoring whether the input devices, output devices, memory controllers, everything is in sync and they're working fine. And then finally you have the application software which is right on top, which is now using your high level languages, so on and so forth, to execute what you would like. The next thing that we look at is abstraction. Obviously, we can write stuff in machine code. But then, because machine code is fairly complex, we would only be able to write simple programs. So abstraction sort of helps us to deal with complexity. It takes away a lot of the lower level tasks that we need to do. So every processor has something called as the instruction set architecture, or ISA, which is sort of the abstract interface between the hardware and the lowest level software of the machine. it basically gives you a peek into how to use the different circuits on a microprocessor and what sort of computations can be performed over there. And it'll allow you to write stuff in machine language. So it also gives you access on how to fetch memory, fetch data from memory, do instructions, how do I put back data, how do I do input, output, so on and so forth. And there are many different standards for this. The most popular ones that you would have probably heard about are x86, x86-64, which is extremely popular amongst desktop machines, IA32, ARM on low power devices, some former ones like SPARC, Motorola, MIPS, so on and so forth. Now, apart from the instruction set architecture which deals with the hardware, you have what is called as the application binary interface. Now, this is the user portion of the instruction. The reason why we need this is that we need what is called as portability across computers. A program which can compile and run only on a single machine is a fairly useless program. What we would like to have is reproducibility and portability. More importantly, sometimes it is necessary to share only binary code and not the raw source code for use in other places due to intellectual property reasons. So if you want to have binary portability in the sense that I am able to execute a code and compile it on one machine, and I should be able to copy that executable and go and run it on another machine somewhere else on my friend's computer, I need what is called as the ABI or the application binary interface. So this defines sort of the standard binary portability across different computers. Thank you.